Up to now in this course, we've been analyzing control systems in the time domain. Now we're going to start analyzing in the frequency domain. Briefly, why would you even want to do that? Some things you want to control or analyze are inherently frequency based, maybe a radio or a radar or vibrations. That's one reason. Another reason is inputs we don't want. Noise is often modeled as as sort of random over certain frequencies, like white noise is over all frequencies. Uh, the noise for your system might be concentrated in certain bands of the frequency spectrum, and we're going to want to reject unwanted inputs or noise. And the third reason is we can use some frequency-based tools to even relate to time-based performance measures. And we'll get into all that, or at least some of that, the latter part. So that's kind of why we even do this. And what does it mean? Remember, you had a system, if you just gave it like maybe a step input or a ramp input, we had the final value theorem that says you'll get some steady state answer. It could be zero, or it could be a constant, or maybe it's just off to infinity for an unstable system with that input. But now, what if we give it a sine wave as an input? There, it's not just some constant. You get more interesting analysis there. So we're going to take a linear and stable system. It's got to be stable. Otherwise, you give it a sine input, it probably goes unbounded. The output goes unbounded. So we'll talk about a linear stable system, and we're talking as time goes to infinity. And what happens? If you give it a pure sine wave input, what comes out is a sine wave in steady state. After you let all the transients die out, you get a sine wave at the same frequency as the input. I think that's a pretty remarkable result. Here's the transfer function. Remember, it's the output over the input. We'll call that transfer function M of S. This is all Laplace transform domain, Laplace domain S. But let's see what happens. You give it an input in a time domain, a sine wave with the frequency of some omega, steady state response, meaning the time response as time goes to infinity, is the same sine wave with the same frequency, but first, an adjusted amplitude of that sine wave, and secondly, a phase shift of that sine wave. And here's the neat thing. Both that gain or this amplitude ratio and the phase shift phi, we can calculate from the transfer function by plugging in j omega for S. And we get a frequency response. And again, it's pretty remarkable. Just plug in j omega through the Laplace variable S, somehow get physical meaning of frequency. So this amplitude ratio, we'll often call it the magnitude or the gain, calculated by calculating the magnitude of the transfer function. And the phase shift, which we often just call phase, is also calculated from the angle of the transfer function. I think the derivations are kind of neat and not all that super deep, but I'm not going to cover it in these charts. You can go to my website. And here it is. Here's my website, and it has the derivation. So here's an example. Here's the system. simple first order system. We're going to make that input a sine wave at a certain frequency. Transfer function is simple enough, 1 over s plus 3. So this magnitude is the magnitude, plug in j omega for this s, take the magnitude of it. The magnitude of a whole thing is individual magnitudes. In this case, you've got a numerator over a denominator. So it'll be the magnitude of the numerator, which is just the real number 1, which is just 1, divided by the magnitude of the denominator. And when you do the magnitude of a complex number, you use the Pythagorean theorem, right? It's the real part squared plus the imaginary part squared, but you don't square the j. It's everything but the j that you square. And you calculate the angle. It's the angle of the numerator minus the angle of the denominator. The angle of a positive real number is 0. The angle of a complex number, you use inverse tangent. It's the imaginary part over the real part, right? That's what this says. So there it is for any omega. Here's what the phase is for any omega. This is the gain for any omega. In our case, the omega was 3, so just plug in 3 for those formulas and get numbers. So if you notice, you're going to get a magnitude and a phase for any omega. Here's like a case of the magnitude, what it might look like. The amplitude at omega equals 0 is called the DC gain. And in fact, it's just the steady state response to a step. You can think of a step input as having 0 frequency of 0. We talk about bandwidth. When you can calculate it, one way to define it is it's the frequency at which this gain is 1 over the square root of 2 of the DC gain. So when the DC gain is just 1, it's going to be the frequency at which the gain was 1 over square root of 2. So that's the bandwidth, meaning it passes through frequencies down there and tends to reject higher frequencies, maybe be where your noise is. And by the way, sometimes these frequency spectra can be found experimentally. You take your system and give it a sine wave input and do that for sine waves at a whole bunch of frequencies, and you get an experimental or empirical frequency spectrum. Sometimes you can do stuff with that, even if you don't know the actual transfer function. A tool we're going to be using a lot is the Bode plot. And what it is 2 different graphs all in one chart. It's the magnitude on top, phase on bottom, both plotted against the same frequencies, where the frequency is incremented in log. So 10 to the 0 would be a frequency of 1, 10 1 would be 10 radians per second, 10 to the 2, 100 radians, and minus 1 is 1/10 of a radian per second, etc. The phase plot, the y-axis or the magnitude of the phase plot is just linear in degrees, but the magnitude of the magnitude plot, the y-axis of the magnitude plot, is also in dB, and actually it'll be 20 log 10 of the actual gain. So here's an example produced by MATLAB of a particular Bode plot. What we're going to do after this video is spin a lot more videos talking about how to do Bode plots by hand, how to interpret those Bode plots, and how to use Bode plots to help you design a control system. So we're going to be spending a lot more videos on Bode diagrams. Um, so that's introduction to frequency analysis and Bode plots. On that